This video is about the create lift chart operator. This operator generates a lift chart from an example set in a classification model. Now, a lift chart is a graphical view that shows how effective a model is in predicting a label when compared just to guessing. To explain the lift chart, I'm going to use other operators to build up the numbers that are shown on the chart. Seeing where the numbers come from is a good way in this case to understand what they mean. Now, I'm not going to explain in detail these other operators, but there are other videos available which you can refer to should you need to. The operators I'm going to use are cross-validation, apply model, discretize by binning, select attributes, rename, aggregate, join, and filter examples. The detailed topics we'll cover, well, first of all, we'll recreate the lift chart manually, and we'll use that to understand what's going on. Once we've got that, we'll then make some changes to the lift chart parameters. So we'll change the target class, we'll change the binning type and number of bins, and then there are some more sort of esoteric presentation things: automatic number of digit, show bar labels, show cumulative labels, and rotate labels. So I have a process. I'm going to run it because I've created a view that makes it a bit easier to have it all in one place. So the process is here. Basically, it retrieves the sonar data set. That goes to the output here, and you're seeing it here. So let's look at this first. The sonar data set has 208 examples. It has 60 regular attributes and a class with the value rock or mine, I think. Yes, there it is. Okay. So this sonar data is passed to a cross-validation operator, where I'm just using that actually to build a model, and the output from that will be a model plus the training data. So I'm going to pass that to the create lift chart operator. Now this is it's going to overfit, because it's what the create lift chart operator does is then apply that model to the example set to produce this chart here. Be aware that the model was built on the training sets, and therefore it will overfit. Nonetheless, that's not really the important point in this video. The important thing is where these numbers come from and how to interpret them. So anyway, the create lift chart does its job, and the output from that is shown here. But then what I'm going to do is recreate some of these numbers here manually. I say manually, using a process, and here these operators here will do that. And the output from all of that will be this, which is essentially a count of various things. But we're jumping ahead. Let's get straight back to the lift chart and the parameters to the create lift chart. So the first thing, let's start with these are the parameters that I'm using to the create lift chart operator. I'm selecting rock, binning type simple, number of bins 10, and I'm selecting all these to be true. These automatic number of digits and so on, these ones here. And the output from that is this lift chart here. And we look on the bottom, we see confidence for rock, there are 10 bins, and we see there's a count up here, there's a line, and there's numbers on this line. Okay, I wonder what they mean. And then yes, on the left there's a count, on the right there's a percentage. We'll try to explain how these come about. So anyway, all very interesting. But what I'm going to do with the example set and the model, I'm actually going to recreate the numbers using these processes. So the first thing is I apply the model to the example set. It's going to overfit, doesn't matter. The labeled training data that comes out will be will have a confidence level associated with it. And what I'm doing in this discretize by binning operator is changing the confidence from a numerical type to be of type nominal in 10 bins. So I'm essentially going to place each example into one of 10 bins based on a simple division of the range of the confidence into 10 equal chunks. Then what I'm going to do is I'm going to select a subset of the attributes. In this case, I'm only interested in these 4 special attributes: the class, the prediction, the confidence that it's mine, which is one of the values, the confidence that it's rock, which is the one I've just discretized. Then what I'm going to do is I'm going to rename various things. So I'm essentially going to remove the brackets from some of the attribute names. So confidence mine becomes confidence underscore mine, and you can see rock and class have brackets removed and replaced with an underscore in the first position. Then what I'm going to do, I'm going to aggregate by class and the confidence that it's rock. Now if you remember, confidence rock is now in one of 10 values, depending on how confident it is. It's not a number, it's a nominal value. And class will be one of rock or mine. So what I'll do is, let's set a breakpoint just before and just after this aggregate, so we can see what it looks like. So here I've set the breakpoint at the point where I'm just about to do the aggregation. So if we just recap, what we were seeing here is a filtered example set with only the special attributes in. The original class is here, the prediction is here, just for the sake of argument. How confident the classifier was is that it's mine is shown here, and how confident that it's rock is shown here. But if you remember, I've put the value in a range which is between 0 and 1, and there are 10 equal ranges. And you can see if I go on the statistics view here and click on this one here rather, and the details, you can see that the nominal values are indeed intervals, in 0.1 intervals, and you can see how many of the examples have been placed into those. So let's continue. So now we're about to do the aggregate. If we look at the parameters to the aggregate, we're grouping by class and confidence that it's rock. So what we're going to be doing is grouping confidence rock and class, which is those two there, and we're going to then look at the aggregation. We're going to do a count of the number of classes, number of rocks, or the number of mines in each case. So let's just do that. Now we've just done this aggregate. Now what you're seeing is a count of the number of entries given a confidence and a class. What this means is that the confidence of rock, that it's between 0 and 0.1, is there are 9 in this situation. So in other words, it was confident, it wasn't very confident it was rock, but there were still 9 that were rock. In contrast, at the far end here, it was between 0.9 and 1. As its confidence that it was rock, it was actually rock, and there were 76 in this category. Okay? So we're going to move, so just think about that for a moment. So we've counted how confident it is, and then we've distinguished between the actual class given a confidence, and we've counted number regardless of what the class is. So, okay, moving on. What I'm going to do is I'm going to now do this aggregation here. Now this is different. We're going to do just the confidence rock aggregation. So this is just going to say count how many were in each bin. So I'm going to set a breakpoint here, and if you notice, by the way, I'm doing this on the original data. So I'll set a breakpoint before, another one after. Now we're about to, therefore, so this is the example set from before the first aggregation, but we've got it back because of this original row here, this connection here. Then we're going to aggregate it, and this time we're counting the number in each interval defined by the confidence rock attribute. So essentially what it's saying, there are 113 examples whose confidence rock is between 0.9 and 1. Okay, and so on. Now we're going to join. So let's just do a breakpoint before and a breakpoint after the join. And the join I'm going to do is essentially an inner join, and I'm going to combine on confidence rock. let's just set the breakpoint. So we're about to join this, which is the count given a certain confidence, with this, which is the count given confidence and class. Let's run it, and we get a single result now. Now what I've done is I've got the count for confidence and rock, where you know both of those, 57. So this is again saying it was confident that it was rock between 0 and 0.1. In other words, it wasn't very confident that it was rock. The class in the original data had mine in it, and there were 57 examples where this was the case. And for the confidence rock only value, there were 66 in total. Go down here, what this is saying, let's interpret this one. This is saying where the confidence rock was 0.9 to 1 and the class was 1, there were 76 examples where in the original data that was true. There were 37 when it was mine, despite it being confident that it was rock. And then the total here is 113, which is the sum of those two there. Okay. Next, we're going to do some filtering. I'm going to basically say eliminate all except where the class is equal to rock. So in other words, I'm going to eliminate these every other row here from this example set. And then we're going to do some renaming just to make things a bit neater, and we're going to rename count brackets class to be the count of a class in range, and I'm going to rename count confidence rock to be count in range. I'm going to set a breakpoint there and run it to the end. So now we've got the final answer, which is this is the confidences discretized into the 10 possible values. Class, this is superfluous now, it's all for rock, doesn't matter, but basically it's saying there were 9 rocks in the original and 66 in total when the confidence was this. Now finish the process and let's look at the lift chart, and what I'll do is I shall move this over here. So let's move this. So let's move it there. That's an easy place to put it. Okay. So let's work along these axes. So first of all, what the lift chart has done is it's basically done the same thing as it discretizes the confidence that the class selected is rock. Let's refresh our memory about the parameters. Here we are. So here's the lift chart parameters. So my target class was rock, so therefore it's decided to use the confidence for rock as this x-axis, and it's discretized that into 10 bins, and I've set this to be simple. Later we'll change this to be some of the other variants, but for now we'll use it as simple. And you can see it's done 0.9 to 1, 0.8 to 0.9, etc. And these match these confidences here. So I've essentially recreated the x-axis of this lift chart by doing my discretization of the confidence that it was rock. Okay, so far so good. Next, let's look at this column here, 0.9 to 1, so this is going to be this one here. We can see a count up here, 76 out of 113. Look, that's those two. And in fact, so the height of this bar is 76 over 113, and this is a cumulative thing, so this will increase each time. So the next one, let's look at 0.8 to 0.9, that's this one here, and we can see that, make this a bit bigger. There were 3 that were rock for this range and 4 in total, hence the 3 over 4 that is there. And you can see in general this is how these are filled in. 2 over 5 is that one, 1 over 3 is that one, 4 over 6, and so on. Then this cumulative line here is basically, you can see that the starts at the 76 over 113, so 76 here out of 113 in total, then it adds on 3 and 4, so essentially the sum of those two is 79, the sum of those two is 117, the sum of these three is 81, the sum of those three is 122, anyway it goes on. Okay, so the final on the right hand side here, this cumulative is essentially saying there were 97 rocks out of 208 in total, and this is saying that when it was confident that it was rock between 1 and 0.9, it got 76 out of 113 correct. So some other parts of this chart, this percent of rock axis corresponds to this line here, so essentially 97 out of 97 rocks have been classified here, and so that's the 100% line. This is showing you how this cumulative percent of rock is being built up. It starts at about 80%, gets to, I'm thinking, about 90%, so I suspect the classifier performance will be about 90% given a 0.5 confidence interval. And anyway, you can, if I leave this here for a while, you can see how this is built up. And basically the interpretation of this gives you a view as to how well the classifier is performing. So it's doing quite well, and it's quite confident for a big majority of the rock examples. And there's a sort of scattering of it gets it wrong for across the whole range actually. So even though it's confident that it's not rock, it's still rock 9 times out of 66 here, I think is what that means. So it gives you an indication of how good it works really. Now let's, if I eliminate that, let's change this now to be mine. Keep it simple. I'll get rid of all of these breakpoints and run it again. And this time the lift chart will be different, because it's obviously the percentage of mine, but the numbers, I mean, I haven't redone the numbers in the example set, but essentially it's just rejigging the numbers from before. Okay, so let's now put that back to rock, and let's change some of these other parameters. So if I change this from simple to something like absolute, run it again. Now, very confusing what's happening. Basically it's trying to put 5 examples in each bin on the bottom, so it's basically divided the confidence into bins where the maximum number of examples in each bin is 5, and you can see each bin has something out of 5. It sort of looks neater from this cumulative point of view, but it's a little hard to interpret because of all these digits now on the confidence interval. In order to make it obvious, you know, how it's divided it up, it has to go to 19 decimal places or some such. Let's make that 50, because I'm a bit easier to understand. Yeah, so now each bin is 50, which is what's shown here, except for the last one, which is 8 in it, so it's 208 in total, and you can see it got 48 out of 50 correct between 1 and 0.99 essentially is what this is saying. And you can see how well it's just basically very confident, gets it quite right, then it sort of, there's some noise I suspect is what's happening. I can change this to be frequency. If I say number of bins 10, let's see what that looks like. Now is it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins. Okay, that's good. Each bin's roughly 20. Yeah, 208 divided by 10 is 21. There we go. So sure enough, roughly, yeah, 21 in each bin, and it's basically chopped up the confidence into 10 equal bins, but the boundaries between the bins are not linear. You can see here 0.97 to 0.99, that's 0.02, that range, whereas this range is 0.04, and this range is between 0.56. So this is a non-linear breakage. We can change this automatic number of digits. Let's change that off, see what happens. In my experience, this doesn't seem to make much difference. I think if you try to restrict the number of digits too much, you don't get visibility of what these boundaries are. So I just do that. Show bar labels, cumulative labels, rotate labels. You'll very quickly see what happens when I turn those off. So the rotate labels means you don't see what's going on. I no longer have labels here as well. And the bar labels have disappeared, so I just leave these all on because, well, we want as much information as possible. Okay, so finally I'll change this back to simple and 10, and I'll run it one more time, and I'll bring the example set in, which I've calculated manually. Here's the lift chart, and here's the example. Oops. Okay, there we go.